Hello again. So far we have studied the time series forecasting. There were four forecasting methods we have studied. But a big limitation is that the first three only deals with stationary data. The fourth one can deal with the trend as well if modified. But none of these can deal with the seasonality. If there is a seasonality in the historic data, it cannot predict it for future. So we learned in our last video lecture that linear regression is the only forecasting method which can deal with seasonality. So now it's time to study linear regression. If any one of you have taken some statistics course in your undergrad or even in this MBA with Dr. Salam Business Research Methods, you would have studied the regression. It establishes relationship between variables. So we've got independent variables and then we've got a dependent variable. And in terms of time series analysis, the independent variable is the time, and the dependent variable is the future demand data. As the name says it assumes that the data falls in a straight line. So what we are interested in, y is the dependent variable, which is the future sales, and x is the independent variable, which in this case for a time series would be time. So all we are interested in is finding a and b. Once we know the a and b, we can simply put it so if we have got historic data for 8 months, we can make it 9 months. The 9th month would predict the sales for the 9th month. If we put x is equal to 10, it will predict the sales for the 10th month. But we need to be knowing a and b. A is the y-intercept and b is the slope. In traditional linear regression, there are bits of calculations, though simple but a bit tedious. It's called least square method that determines the parameters a and b such that the sum of the square error is minimized. That's called a least square method. For this chapter, we won't be going into the details of this one because we assume that you already know this thing. You have either learned it previously or you learned in another statistics heavy course for MBA. So what we'll be doing, we'll be finding this A and B through an alternate way. What was an alternate way we've already discussed previously is when we fitted a trend line and then we right clicked and we clicked on the equation. So this is an equivalent of a and b. We got y here, this is ax plus b. So a in this case is 3.4571 and b is 48.28. So very simple. If you've got access to Excel, you can get rid of all those tedious calculations. Just right click and you'll be getting a and b. How does Excel do it? We'll quickly go to the Excel sheet and talk about this thing. So simply select go to data analysis tab. In the data tab, go to data analysis. Then at the bottom you see regression. So it's a tool which does the regression analysis. Click on OK. So you have to give the Y range, which in this case is for lilies, it is the 14 weeks past or historic sales for lilies. Then we've got X, which is the time here. Then all you have to do is to mention where you want this results to be displayed. You click OK and there you get. So here is the X variable, which is A, and here we got the intercept. So very easy. The same if you click right click on the so if you right click on the graph that I showed you here and see fit a trend line here and then choose an equation for this, it gives you the same equation which you can get through the formal regression analysis of Excel as well, which is the same way as the theoretical calculation that we normally do in a statistics course. So if you see the equation is the same, y is equal to ax plus b. So this is A and this is B. if you're doing it for some project, for this particular course, we are happy to for you to use Excel and calculate A and B from there. And if it's an exam question, so you'll be given equation, you'll be given a linear regression equation for a particular model, so you can pick A and B from there. So you'll be saved doing those tedious calculations. Now the next thing is, we know that a time series may have many components of its demand, could be trend, average, seasonal. The book also talks about cyclical autocorrelation that we won't go into. Random is anything that you cannot explain is a random variation. So the point here is that we learned previously that linear regression could predict seasonality component for future. Now here we'll be using linear regression to calculate or predict a future demand where there is a trend and there is seasonality. How to do that? First we'll have to decompose our existing time series, existing data. How can we decompose our existing data? We need to separate the seasonal element and separate the trend component from the original historic time series, and then based on that we'll first project the trend component and then multiply the previously calculated seasonal component with the future trend predictions, and that will give us a future prediction that has both the trend component and also the seasonal component. This is the overall theme. The next slide we'll go to the specific details of how to calculate or how to find out a forecast for future that has both seasonal and trend components. The first step is simply plot the existing sales and past data on an XY graph that we have done with the roses and lily example as well. So once we plotted the XY graph, the data on XY graph, we need to fit a trend line and get an equation for it, which you could so easily do on Excel. And if it's in a question in exam, you'll be given an equation like y is equal to 176 plus 52.3. So you'll be required to hand fit that equation on your graph, which is simple. Just start your line from 176 on y-axis because it's y-intercept, and then extend it between the points which are already on the graph. Now having hand fit a trend line, we've got two things on our XY graph. The first thing is the actual data that may include the seasonality, may also include the trend, but now we have plotted a trend line as well. So having plotted the trend line, the next thing is that you would like to separate the trend component from the original or actual data. How can we do that? We'll use the trend equation. So this is trend equation. We'll put x is equal to 1. That will give us the demand that only has the trend in it. So we'll put x is equal to 2. That will give us the trend component for the second time period. So if we've got 5 or 6 time periods, we'll keep putting in the corresponding value of x, and it will give us the corresponding value of trend component. So this is a trend equation. So again, now we've got two sets of data with us. A is the actual time series and the second one is the trend data. If we divide the actual data by the trend, we get the seasonal factor. And if you've got more than 1 year, we need to get the average seasonality factor. So for example, we've got data for 2 years, 2011 and 2012, and we need to have two seasons, Q1 and for 2011 and Q1 for 2012. We need to add the seasonality factor and then divide by 2. That will give us the average seasonality factor, and then we can repeat the procedure for all the quarters of these 2 years. The sixth is, that's now projection. having separated from the first 5 steps, we separated the historic seasonal element and historic trend element. Now we go to the future prediction part. We've got a trend equation, y is equal to 176 plus 52.3. So now we'll put the x that corresponds to a future event. For example, we've got a historic data for 8 months, so we'll put x is equal to 9. That will give us a prediction for future month, that's the 9 month. So that will be only the trend component. If we multiply the average seasonality factor to the future predictions for trend, that will give us the complete forecast that has a trend and a seasonal component. So multiplying the average seasonal factor that we obtained from historic data, if we multiply it to the future trend, that will give us the future forecast that has both trend and seasonal component. So we'll be repeating all these steps for an example. The example is in the next slide. So we've got data for 2 years. So this is 2011 and this is 2012. We've got 4 quarters, and the actual sales of a company for the past 2 years are given like this. So in these slides I've done calculation as well, but we'll go on Excel and solve it for you. So we've got 2011 data, we've got 2012 data, and we need to be predicting for the quarter 1, 2, 3, 4, 2013, but I've listed those in a sequence. So this is for the first 4 quarters, then the next 4 quarters are mentioned like 5, 6, 7, 8, but these are quarter 1, 2, 3, 4 year 2012, and then quarter 1, 2, 3, 4 year 2013. So the first thing is that we need to plot this on an XY graph. So we'll just do that. Let's go here. So that is an X and Y graph, this past sales for 2 years. The next thing is we need to fit in a trend line here and also display equation here. So we notice here that the equation has it's 52.262x plus 176.07. So our steps, if you go back to the PowerPoint slide, our having fit an equation here. The third step is that we need to calculate the trend component. So what I'll do here, so I'll quickly write here, A would be, A is equal to 52.3, I've rounded off, and then B is equal to 176.1, let's put it that way. So now we'll be extracting the trend component from the actual for the past 2 years. So we'll put, so that will be y is equal to A into x is the time plus the B, and because we, okay, so let's do some Excel thing here and here as well. Those who are familiar with Excel would know what I have done, but I won't go into the detail. So now we calculated the trend component from the actual data. So this is the total data. Now I've just extracted the trend component out of it. Next step is I have to calculate the seasonal factor. Let me denote it with an SF, seasonal factor. Seasonal factor is simply actual divided by the trend component. So this is the seasonal factor for this quarter. Now if I drag it down, I've obtained the seasonal factor for all quarters. So because I've got more than 1 year, so I need to take the average seasonality factor for each quarter. So average seasonality factor would be ASF. So what I have to do is simply take the average of the seasonality factor for the first quarter of 2011 plus the first quarter of 2012. Yes, it's 305, and then press enter. So that will give me the average seasonality factor for quarter 1. If I drag it down, would have the average seasonality factor for the quarter 2, quarter 3, quarter 4. So now I've got the uh, average seasonality factors for the 4 quarter. Now I need to go to step 6. I need to go to the future and predict the trend component for it. So all I have to do is to drag it down. So now I've obtained the trend factor for the 9th time period, which is quarter 1 of 2013. This is quarter 2 of 2013. This is quarter 3 of 2013. This is quarter 4. And if I multiply the future trends with the average seasonality factor, so I'll get the final forecast. So let's give a forecast that includes both trend and seasonality factor. If I go here, simply multiply this one with this one, and then if I drag it down, I will have the future forecast for quarter 1 of 2013, quarter 2 of 2013, quarter 3 of 2013, and quarter 4 of 2013. So this is how I've calculated. Very easy in Excel, but in exam you won't have the services of Excel, so simply multiplication and addition you'll have to do it yourself on a paper. So I would highly advise you to follow the same example. Try to do it on a piece of paper. This is a very important question for your final exam. So let's go back to the PowerPoint slides. So these are the instructions that I've done on an Excel sheet as well. This is the question. The first thing was that we plotted the graph. So you'll have to plot an XY graph on paper and then plot the 8 data set here, then hand fit an equation based on this equation. So start from 176 and then try to hand fit it so it fits in the existing data. So this is step 1 and 2. Then from this trend equation I calculate the trend component, and then I calculated the average one, and then based on this there will be slight differences with these, but they are just because of rounding up and rounding down. So essentially the essence is the same. The answers do match up. So this is how we can predict. It is important that we take into account the seasonality factor, because the total might be the same, but the requirements of quarter 1, 2, 3, 4 vary a lot. So if you stock too much for the quarter 1, where if you stock an average average quantity for the 4 quarters, we may be stocking too much for 1 quarter and stocking less on another quarter. That will be stocking inventory excessively in 1 quarter, and we may be under stock for the 2nd quarter. So it is important that we include the seasonality calculations for future predictions, and we have just done that. It is very important that we practice this question here, and at the end of this lecture I'll give you some questions to work out before our next class. So this is linear regression to calculate the seasonality and trend factor for future predictions. Okay, the next thing up is that the first and very important rule about forecast is that no forecast is 100% accurate. There would always be errors. This is what we found out with the exponential smoothing, and we talked about the thing that exponential smoothing is very accurate because it takes into account the error that was there in our last prediction. So actual demand minus previous forecast was actually an error. That was a deviation. So what we thought would be our demand and what actually was the demand. So that's a deviation. You also notice that it could be negative if the actual is was less than the forecast. It will be negative, and it could also be positive if the forecast was more than the actual, or vice versa. So in mathematics, what we do when we say absolute, then we ignore the sign. So even if it comes out to be a negative thing, when we say absolute deviation, we would not take into account the sign. So mean absolute deviation would be absolute deviation. We are ignoring the sign. If the forecast is more or the actual was more, we are just ignoring the sign. And mean absolute deviation would be the sum of all absolute deviations divided by the number of forecast. So one way to check how good our forecast was to calculate the mean absolute deviation. That is, calculate the sum absolute deviation and divide by the total number of forecast. This is the formula. So absolute, whenever we write this sign, around any term, so that will tell us that it's an absolute calculation. So we won't take into account the sign of this, whatever sign comes out of the calculation, and we'll be dividing it by the total number of deviations. That will give us the mean absolute deviation. So let's go further and do an example that will make everything very clear. So this is the formula. So this is the actual demand, this was the forecast. So we forecast that our forecast was that 80 units and for January, but actually it was 100 units. So there was a difference of 20. So that has to be positive. Then the actual was 94 and our forecast was 84. Then again 10. Then there's a difference 20 here. But now the forecast was more than the actual one. It should have been negative, but we are taking it as a absolute deviation. So we'll just write the deviation. Sum all these deviations together, we get 90. So how many forecasts we have? 1, 2, 3, 4, 5, 6. So 90 divided by 6 will give us the mean absolute deviation. So mean absolute deviation for these forecasts, these 6 forecasts, is 15. That is one measure of knowing how accurate our forecast is. Ideally it should be 0. So it is 0, that means that there was no difference between our forecast and the actual demand that we faced. And the lower it is, the better it is. Another related measurement error yardstick is mean absolute percent error. Its utility comes from the fact that it relates the mean absolute deviation to the average demand. For example, if the calculated mean absolute deviation was 10 and the average demand was 20, so 10 divided by 20 would be 50%. Whereas the same mean absolute deviation of 10 and the average demand was 1000, the mean absolute percentage error would be 1%. So just a measure mean absolute deviation or math is a partial measure. It does not relate to the average demand or how good our forecast was relative to the magnitude of the actual demand. But going for MEP or mean absolute percent error, it would relate our absolute deviation, mean absolute deviation, to the overall magnitude. So in this case, though the mean absolute deviation is the same for both these cases, but the percentage for here is 50% error, it's just 1%. So that gives a good measure of how good our forecasting was. Okay, so that brings an end to a bit heavy lecture. But if you followed it by repeating all the calculations with me, so hopefully it would have been very useful to you. If not, I will, in fact it's a must. You have to, for your own good, if you want to do well in your final exam, there is exercise that you must complete before attending the next lecture. Please do it, and if you've got any questions, we can take up whenever we meet after this online video session. Thank you very much.